When most people talk about AI these days, they're talking about generative AI. So this is large language models like ChatGPT, Gemini. I'm going to give you a quick history of how we went from the 1950s all the way up to these chatbots that can do some pretty amazing things, give you a look inside how they actually work, and then give you some tips for prompting, prompt engineering, how best to use them. If people can learn one thing from all of this in a post-AI world, I believe that these are the two most important skills you can have. They both have to do with critical thinking. So determining what are the right questions to ask. This is not as simple as you might think. And then also evaluating the responses that you get. You cannot always trust the output that you're going to get from an AI. We've seen that in other machine learning models as well. Large language models are no different. So you want to be able to critically evaluate what you get and then know how to apply that to the task at hand. We've talked before about the different types of data. So previously we've been focused on tabular data, which we can look at any piece of data in context within the data matrix and know what it means. Now we're talking about language data, which is really a sequence. So it's sequences of words make up sentences. As we'll see, computers need to translate everything into numbers. So you end up with really a sequence of numbers is how the computer represents that. But in general, the transformer architecture that powers large language models today is really a generalized sequence to sequence model. This is why it works well on other types of modalities as well. So it's becoming really good at generating music and images and other things like this. So sequential data is what we're focused on, particularly language. Another thing to consider is that structured data or tabular data is usually much more well defined. It has a format as opposed to unstructured text data. So a lot of the models are trained, for example, on content from Wikipedia pages. If you compare these two types of data, the Wikipedia page has images, it has headers, labels, all call outs, all kinds of different things. So there's a lot of preparatory work that goes into kind of cleaning this up. So when if you're just focused on a text model, you would kind of clean that up and just give it the pure text that you want it to be trained on. But language data can be tricky. There's a lot of challenges with these sequences of words and sentences. So here's kind of just a fictitious example. It's a paragraph of text talking about Dr. Patel, talking about her sustainability plan in a town meeting, and then referencing different aspects of it. So there's a number of pronouns and referential words, even in just these two simple sentences that refer back to other aspects that were discussed previously. She refers to Dr. Patel. The concerns that we're talking about in the second sentence are scoped by the first sentence. We're talking about concerns for sustainability, the environment, etc. So this is just in two sentences. You can imagine across a whole document or a whole report that large language models, which have very large context windows these days, can process. So the attention mechanism that we'll talk about is the key part of transformers or language models that allow it to figure out what words should I pay attention to with respect to others. So it's really impressive what they can do now. Okay, but how did we get to this point? So in the beginning, the focus was on grammar, linguistic rules, and linguistic theory. Here's an example of a context-free grammar where you can take a sentence and decompose it into its parts. Overall, at the top level of the sentence, first has a noun phrase and a verb phrase, and then you can see a noun phrase can have a determiner like the cat or the dog, and you kind of break down this hierarchy. You just come up with all of these rules, and so you can see if you're trying to sit down and write all of the rules that describe how we can communicate, and this is more formal language, of course, there's many variations, there's slang, you would be writing rules for a long, long time. Now, these systems did have success in limited domains, not to say they weren't valuable, but you can see here, this is a very simple example, but as soon as we add a new word to the vocabulary or vary the sentence structure a little bit, our model's going to start to break down. Initially, one of the focuses was part of speech tagging. So as a part of breaking that down, we can identify in this sentence, the quick brown fox jumps over the lazy dog. We can see where are the adjectives, the nouns, etc. So we're creating this very structured hierarchical format of the sentence. Of course, all of these references that we're talking about aren't always crystal clear. There are some ambiguous ones. In this sentence, I saw the man with the telescope. So does that mean I used the telescope to see the man, or the man that I saw was using the telescope? So from context and our world knowledge, we as people can discern these things within the context of a conversation. But teaching computers how to do this can be pretty tricky. And so that's why taking vast amounts of text and training over those patterns that the models are going to discover, help it to be able to do that. The next big paradigm after linguistic patterns or structures and focus was statistical methods. So one of the key mechanisms or concepts there is n-gram. N being the number of words I'm going to consider, and then the words that show up consecutively or in a row. And you look at probabilities. So here's an example. If I'm n equals 3, so what you would call a trigram. If I've got the words the big, what's the probability? What word is going to follow that? And so here we're showing the probability of the next word being apple, the big apple. That would be how many times have I seen that phrase over all of the times I've seen a series of 3 words that start with the big. That would give you the probability. And so even something simple like this it becomes very useful. You can see in spell correction, I went to the C or C, so those are homonyms, but which one is the correct one? So in the context of where the model has seen those patterns before, I know that the ocean or the sea is going to be more commonly used there, and so I can choose that as got a higher probability. So as we've discussed before, computers and neural networks need our information, our input features, at some level to be converted to numeric form. So the question is, how do we do that? How do we take text, convert it to numbers? So things that we want to keep in mind: the order of the words that they show up in the sentence, how frequently they show up, in a given document, if that's what we're looking at, and also compared to all of the documents that we're considering. And then the semantics, like what do they actually mean, which is such a critical concept. So it wasn't until later that the semantics really came in, but we're going to look at a couple of techniques that researchers started out with and actually became pretty effective in some use cases. So for our examples here, we're going to consider this simple set of sentences: the cat sat on the mat, dog sat on the log, the cat and the dog sat together. So this is a very small vocabulary. It's almost like a toy vocabulary, but we're going to use that for a few examples here. Okay, I've got here a Python notebook where I've defined my sentences. And the first thing I'm going to do is calculate the bag of words. So you can see here, I've got a data matrix now with each sentence and the words and their counts in each of those sentences. So the word the is pretty common. It's going to essentially become kind of meaningless in the end. And you can see here the counts across the 3 sentences. So this is a very simple statistical measure. Doesn't know anything about meaning, but it has been used successfully to some degree in text classification and clustering use cases. Now what we're going to do is take those vectors and plot them. We're going to use PCA to convert it to a 2-dimensional, reduce the dimensionality to 2 dimensions so that we can plot it. And here, if you look, you've got sentence 1 and 2, which are a little more similar than the others, right? They're both talking about where the cat or the dog sat. Sentence 3 is a little bit different, so it comes out kind of over on the right side, a little bit farther away on a different dimension. So that's kind of interesting. Again, this is just a very simple toy example where there's limited things we can pull out of this, but you can see some of the concepts kind of get flushed out. The next thing we can do is look at the cosine similarity or cosine distance between our sentences. So cosine similarity we talked about before. It's a measure from 1 to -1. A 1 means the vectors are pointing the same direction, -1 completely opposite. The distance is actually 1 minus that value. So distance, the smaller number, the closer together that they are. And this is a symmetric matrix, so each sentence on the diagonal, each sentence compared to itself is going to be 0. There is no distance. You can see really the main thing to pull out here, this is validating our intuitive notion from looking at that chart before, that sentence 1 and 2 are a little bit closer together, a little bit more similar than 3 is with the others. So the cat sat on the mat, the dog sat on the log. Those are more similar than the dog and the cat sat together. So not by a lot, but by a little bit. So some of those concepts start to come out. In a large vector embedding space, you would see much more meaning coming out of these. The next statistical measure, and this one is used in search, it's gotten a pretty good amount of use, is term frequency, inverse document frequency. And there's a few math formulas on here, which I wanted to be explicit and show you what's going on. But here's the intuitive notion. TF IDF is 2 things multiplied together. The first one is term frequency. If I'm searching for a word, how often does this word appear in that document or in that item? Okay, so the more times it occurs, the higher score it's going to get, the more likely it is to be returned from a search. Document frequency would be how often does it appear across the entire corpus, the entire set of documents that I'm considering. We take the inverse of that. Why? Because if the word shows up everywhere, then it's not as important in any one given place. So the higher document frequency actually would bring our score down. So the product of these is what you call the TF-IDF score. So let's look at our example now. First, I'm going to calculate the TF-IDF scores, which you can see here for our very small set of sentences. So here's a few things. So cat has the highest score on the first sentence where we're talking about the cat sat on the mat. It shows up in the third sentence as well. It's got a little less of an importance because that sentence references both the cat and the dog. Log, for example, only shows up in sentence 2. It's got a very high score there. And so you can kind of get the idea. Now, if we take these scores and do a similar thing, look at a heat map for these scores, you can see this kind of visually pulls out which words are more important in which sentences. So in the darker blue, log and mat only show up in those sentences. They're the most important. And then the medium shades of blue, you can see here's our cat example. The numbers are there. The visual, the heat maps are a very nice way to kind of quickly at a glance see where things are important or not so important. So one of the big breakthroughs was word embeddings, this concept where we take a word, and you can take larger bits of text as well, entire sentences, but you convert that word into a large high dimensional vector. I've got some sample data here. It's a very simple embedding model. It has 384 dimensions, but typically these will have 1,000 or more. So a single word or phrase or sentence, paragraph, whatever, would be converted to a set of 1,024 numbers. Now, what do those individual numbers mean? Well, that is learned through a training mechanism. They're actually neural network weights is where they come from, but that allows the model to understand different dimensionalities of words and their meanings. And you have a much better ability to look at which words are similar, how they relate to each other, because their positioning in that high dimensional vector space has importance, which we're going to look at in a minute. Now, we can only visualize very easily in 2 dimensions, sometimes 3, but here are some sample sentences similar to the ones we just looked at, where I've reduced the dimensionality to 2 dimensions, and you can see where they fall. So on the left side here, the cat sat on the mat and the cat likes to sleep on the mat. Those sentences are pretty similar and they appear very close in the space, in the vector space. A bird flew over the log is kind of different, so it's over on the other side. And you can see how this kind of falls out. Again, this is using dimensionality reduction, so you're losing some fidelity, but this does, it picks the most important dimension. It tries to capture the most variance to show you the most important differences between things in the embedding space. And this idea, this concept is really what drove the ability for transformers, the transformer architecture and large language models to work. Because once you've got this high dimensional representation of the concept, you can use neural networks to basically go through training, which we're going to talk about in a minute, and be able to predict the next token. Embedding vectors are important, and this is the canonical example of why, because when you move in different directions as well, you get a semantic meaning. So this here, so king, if you take the embedding where that lives in the space, subtract the embedding for the word man, and then add the embedding for the word woman, you end up at a spot in the embedding space that's near the token queen. So when you move in particular directions, you can adjust the meaning of tokens, and this is what happens when the language model is reading sentences or processing sentences. You see an adjective or a modifier, it can adjust its interpretation of that concept. Before we get into the details of that, I want to point out that these generative AI models are, whereas we used to create very specialized models to do specific tasks like sentiment analysis or the part of speech tagging that you saw, these foundation models are able to generalize to a large degree and perform lots of different natural language tasks. So they're very good at translating from one thing to another, whether that be from an English description of what I want to Python computer code, or it could be from English to Spanish. And also, as I'm sure people are familiar, you can use AI chatbots to answer questions, summarize text. Here's kind of an attempt to summarize what those use cases are, but there are many, and they're very, very good at a lot of these tasks. So the modern era, if you will, is the deep learning era. And while statistical methods still have value, Deep learning using very deep neural networks is really where natural language processing has been focused. So that falls within, or I should say generative AI falls within deep learning. And then when you're talking text input, text output, that's an LLM. There's other types of generative AI models. In this particular lecture, we're going to focus on the language models. And this image here, again, just kind of calls out that traditional AI models, where we would call narrow AI, are focused on a particular task. So you can use supervised learning, some of the techniques that we've looked at previously to classify an image, unsupervised learning to do segmentation, clustering. Now, foundation models that we're looking at here, they are trained on huge amounts of unstructured data, and then they can be fine-tuned for particular tasks. So the chatbots obviously are trained to be very good at answering questions. You've also got image models and other types of specialty models as well. There is an interesting story behind how this all got started. So this graph here, if you look at the blue line, that is the performance of a model while you're training on the test set. So what happens is, as you start training, you get a lot better on testing out your model. And historically, there's been this kind of trough at the bottom where now you start to overtrain. And what the model ends up doing is just memorizing the training samples that you've given it, and it starts to perform worse on data that it has not seen yet. What actually happened in this case is from a training run that the first time that I guess has been publicly documented perhaps, where they let the training run for a long, long time, the test performance after a while then started to improve. And that was kind of one of the key, I guess, revelations, if you will, behind the story of language models. If you're interested, you can go look up this story, but essentially this story talks about OpenAI accidentally left their experiment running, I think maybe over a weekend. They let it go for days instead of just hours. And that's where the term grokking comes from. So that's where, after seeing worse performance, then the model eventually got better. So through lots of training, lots of data, the model improved. And that led to what we have today, which are GPTs or transformers. So the name ChatGPT, the GPT does have meaning. It stands for Generative Pre-trained Transformer. So generative meaning that it's creating new output. The pre-trained, we've talked about that. We've given it tons of information so it can learn the language patterns. And then the transformer part, and again, that really is almost a generalized, given a sequence of inputs, I can create a sequence of outputs. But this idea first became or was first published in 2017 in a Google paper, Attention is All You Need. Attention being the attention mechanism, which helps us to look at that input and figure out, kind of resolve that ambiguity that we talked about earlier, deal with some of those challenges, and look at what parts of that input should I most focus on as I generate each new word in the output. Now, what does pre-training actually consist of? So when I take, for example, those Wikipedia pages, what do they do with them in pre-training? So there's two types of training that happens here. One would be masked language modeling, but causal language modeling, the second one, is what GPTs use. So basically it goes through the document word by word, and it just takes the first part, given its context window, how many words it wants to look at a time, and given that, tries to predict what the next word will be. And it's going to be wrong at first, and then it's going to adjust its weights through training, and it's going to continue to do that through the entire document over the entire training set. And eventually it will get very good at predicting what the next word will be because it's seen those patterns before. So at the most basic level, and I don't want to, this is very much a simplification because people do get into debates about this, but at the most basic level, an LLM is a predictor. It's predicting what the next token is. So critics will say, well, it's just a stochastic parrot. It's just repeating back, what it's heard before. And then proponents of large language models will say, well, no, there's intelligence that emerges out of that ability. And I'm going to show you some subsequent training that goes on to kind of add in more of that intelligence, and then more recently the reasoning that we see in reasoning models. So after that first initial training where you're just, masking the next word and predicting it, you've got a model that understands the patterns of language, but is not very good at answering questions. So this is a website where you can use some base models. This is a Llama 3.1 just base model. It hasn't been fine-tuned yet. hasn't gone through reinforcement learning. So my prompt was, what are the best things to do in Orlando this time of year? And it talks about some things that generally make sense, but it's this kind of long, rambling answer. Not completely coherent, but you can get the gist of it from reading what it's saying. But it's not what you kind of response you would expect to get. For example, if you went to ChatGPT today and asked the same type of question. Now here, I'm asking the same prompt of the Llama fine-tuned model. This is the 405 billion parameter one. And you can see it's a little bit more personable. Even though it doesn't know specifically what time of year it is right now when I'm asking, it makes a guess, and then it gives me a bullet pointed list with some ordering of perhaps what it thinks would be the most attractive or the most desired destinations. So it's much better at answering questions. So fine tuning actually happens by giving the model samples, examples of here's a question and here's an answer. And those are kind of, at least initially, they were reviewed by humans. Now that language models are getting better, we can start to generate more of those. But the way that those examples answer questions is how the model is going to learn to do that. And that explains to some degree why you see a little bit of a different, I'll put in quotes, personality from the different models. Some models will give you more in-depth and detail. Some will kind of be more just short and to the point, or they have a different tone of voice. All of that was learned through this fine-tuning. Because if you think about it, just the basic patterns in the English language probably will be mostly the same through all of these training processes. But the fine-tuning is where each model behaves in a little bit different way. And that's why some models are better to use for some use cases than others. Now let's talk about what is the basic design for GPTs. So the first step is to take that prompt that you give it and parse that into tokens. The tokens are just numbers for the different parts of language that the model sees. Oftentimes that's entire words, but if it's really common portions, fragments of words, the token might represent that. But you end up with a long sequence of numbers that represents what your prompt is. It's going to take those tokens and convert it to the embedding. You remember we saw it's a long series of numbers. I showed a chart where we did a 2D projection of it, but oftentimes this is 1,000 or more dimension vector. So now we've got a high dimensional, more semantic representation of that prompt. We don't want to lose the order, so we add some information about what word came in what order in the sentence. We send that through an attention mechanism, which says, okay, which parts of this input are most important for me to focus on as I go about producing the answer. And then there is a kind of a more traditional feed-forward neural network that does the processing. And eventually we get to a point where we have probabilities of what is the next word or token that I should output. And there's different algorithms for then actually what to decide. Sometimes it always takes the most probable, but you can also, if you want the model to be more creative, have it vary a little bit. Sometimes it might take the second most probable token. For example, if you're asking it to write a fictional story, a poem, something like that. But that's the basic idea of a GPT. So an important point to consider in GPTs is that they look at the entire input all at once, and that was a big breakthrough of the attention mechanism. It sped that up as opposed to having to do it sequentially. However, when it produces the output, it still does that one token at a time. So it'll produce the first word. So the response might start with the. It'll produce the, and then it'll go through the whole thing again and figure out what word comes after the. And it keeps doing this until it produces an end of response token or the equivalent, and then it will stop and will give you that answer. And this is why you see the responses from language models often kind of get streamed to the screen. They don't all show up just at once, and that's because the output generation is a sequential process. And the probability of each word being generated is takes into account all of the input plus every word that is already generated so far. Let's look briefly at the attention mechanism. So it produces scores, and what that does is it starts to weight differently the different tokens and what should play a bigger role in looking into that probability. And the attention scores, every input token is compared to every other. This prompt here, I just said the capital of Florida is, hoping that the model will produce Tallahassee. And if you look, this is going down token by token. The rows are going to add up to 1. So when there's just a single token, all of the probability is 1. All of the attention is paid there. So really look at these lower couple rows, and you can see where you get to like The importance here is that we want capital and Florida to be related so that we don't just look up any capital. We specifically want the capital of the state of Florida. And if you look in these rows here, capital and Florida, where they intersect in the table, do have a little bit higher attention score than some of the other words. And so that's good. That's how the model will get to a correct answer. This is the overall transformer architecture. So we talked about converting the input into embeddings and remembering what position each word came into the input sequence, and the attention mechanism and the network. So there's actually multiple of these. So it does that, it runs through that whole process, parses the input. Okay, now I'm going to start to generate output tokens. And every time there's multiple what are called transformer blocks, which do both attention and this neural network. So these are very large networks. That's why when you see models are referred to the number of parameters, which are the number of learned weights that are attention parameters that are within these networks, they're in the billions now. They're very, very large networks. It can be difficult to understand what's actually going on inside of these networks, but this is the architecture that they use. Now, more recently, there's been what you could call the third phase of training, which uses reinforcement learning. And the reinforcement learning has been shown in some cases to help what we think of as the reasoning ability. There's ChatGPT-03, a reasoning model. DeepSeek is an open source model. It was one of the first breakthroughs in this area. So there's lots of different approaches that these models use. Best of n, so in this architecture, there might be 4 or 8 different runs of the model that all come up with potential answers, and it's going to take the best of those based on some criteria. Then you have beam search and look ahead search. So there's a number of different considerations here. So one thing would be if at some point in the process of predicting output tokens, if a wrong token is predicted, you're going to end up with ultimately a wrong response. So look ahead can help try to combat that issue. But all of these are different ways to kind of give examples to the model and help it learn over the distribution of predicting these tokens. What's the best way, the best path to get to a correct answer? It's actually really interesting the things that are doing. There is some research to show that the reinforcement learning here is really helping narrow down the search path to get to the better answers. But some of the really effective domains that this works in are where you can easily verify the answer. If you're talking about a domain where you need a human to review the output and kind of rank it or score it, that of course takes time, money, resources, etc. But if you think about having a model write software or code, that can more readily be verified. We can test out, does the code compile or is it valid syntax? Does it run and produce the expected result? Likewise, in math problems, for a problem that we know the answer, we can try many different runs of the model and reward the ones that produce the correct answer. And then we can reward even more the runs that produce the correct answer in a shorter amount of time. This is an example from when DeepSeek first came out. Give it this math problem. What is the last digit of this sequence of subtractions? Now, you can of course do the literal subtraction, but a smarter way to do it is, and the model actually figures this out, is if you just subtract the ones digit, you'll get what is the last digit. You don't need to be concerned about the others. And you can see there's a think token there. And so this is something that DeepSeek started using. And really these are intermediate tokens. So the model is producing these intermediate tokens to try to get to the correct answer. From their paper, they called out this moment where in terms of thinking, the model actually said, wait, this is an aha moment. So it reached a point where it kind of paused figuratively and started to rethink what it was doing. So very interesting to see how this kind of intelligence, if you will, emerges from these reasoning models. I want to talk briefly about a few prompting techniques that you can use to get the most out of using language models. One of the most important is if you're doing a task and you are able to give the model an example of how to do the task or what you want the task to look like, you want to do that. So a 0-shot prompt would be asking the model to do something but not giving it any example. It's going to entirely rely on its learned knowledge from training. A 1-shot would be I give it one example, and then few shot if I can give more than one example. This is a chart from an earlier paper, but it basically calls out the important point here is that going from 0 to 1, just giving one example, can drastically improve the performance of the language models. And then of course, Adding more than one example, it performs even better. But even just giving one example, if you can do that, the models, what happens is called in-context learning. And so even though it hasn't perhaps been trained on that example, because it's in the prompt, it's in the context that's being considered, it can leverage that when it provides your answer. Another foundational prompting technique is called chain of thought. And the basic idea here is that the more intermediate tokens that the model produces, it improves the probability that it will continue down the path to get to a correct answer. So a direct prompt would be, given the input, I go kind of directly to trying to give an answer. In the case of that math question that we saw earlier, instead of going through the long thinking process, it might just arrive with an answer and give us a number. So here, this chain of thought is an example where, okay, first we're instructing the model to do some recall, so retrieve some relevant information, perhaps from your learned knowledge, do some comparison, and then make an inference. So there's two variations here. One, and the initial research had found that just by adding the phrase think step by step, improved the results on a number of tasks in your prompt. So that's a pretty easy and fast thing to do. Now, many models are starting to build this in, if you will. Certainly the reasoning models, you don't need to say think step by step. It's already going to be doing that. But in any model, if you know the process you want the model to follow in order to perform your task, spell it out. You can give it the problem description and then say, first, I want you to do this, second, do this, etc. And you'll have a much better, more likely to have a much better outcome. Finally, there's our settings on large language models that kind of control the dial on that probability, that selection. Remember, the model goes through and it figures out what are the likely next tokens to be output. So the most common is temperature. And not all of the user interfaces on the web, unfortunately, make this easy to access. But the APIs, if you're using them, you can define specifically what the temperature should be. So a higher temperature would be more creative. That would mean it's more likely to pick less probable words. And so you would use that more in creative settings. A lower temperature you would use if you want strictly factual responses. Two other, a little bit more technical parameters are top P and top K. So in terms of what tokens should even be considered at all, top P would say, okay, well, once the cumulative percentage gets to a certain amount, then stop there and then just pick from this list. Top K would be, okay, just take the top K number of words, and that's the only ones that I'm going to consider. All right, that was a quick run through of the history of natural language processing and large language models. I hope that was helpful. I'll see you in the next video.